Hello everyone, this is Rui PCB, your trusted PCB partner. Today our topic is 4-layer board crosstalk control, interlayer crosstalk analysis control, and advanced strategy. Welcome back to the 4-layer board crosstalk control course. In the previous video we learned about the basic principles of crosstalk. In 4-layer boards, besides crosstalk within the same layer, we also need to pay special attention to crosstalk between adjacent signal layers. Today, we will take an in-depth look at this type of interlayer crosstalk and learn how to effectively control it during design and routing. So let's first take a look at the aggressor line in crosstalk, the victim line, and then mutual inductance. How does crosstalk between adjacent signal lines form in a 4-layer board? Let's look at the standard structure of a 4-layer board. Do you still remember the standard structure we discussed before? Signal, GND, power, signal. The signal layer L1 top layer and L4 bottom layer are separated by the GND and power planes. The signal layers on both sides are isolated from each other by the power plane in the middle. The mechanism of interlayer coupling. Even with ground and power planes serving as isolation, there will still be some coupling between signals on layer 1 and layer 4. This coupling mainly occurs through the fringe fields between the two planes and via holes. When the bus on a signal layer does not have a continuous reference plane beneath it, for example, when it crosses a power split region or the signal routing is close to the edge of the plane, its electromagnetic field may leak to adjacent layers, causing deformed crosstalk. Taking this board as an example, you can see that there are almost no traces near the edge, which avoids crosstalk caused by the edge effect. Why is interlayer coupling so important? Although crosstalk caused by interlayer coupling is usually less significant than that within the same layer, for sensitive signals with high frequency and low voltage swing, it can still cause performance issues. This is especially true when the signal layer is split, has many vias, or overlaps with distant layers. Under these circumstances, interlayer coupling becomes even more pronounced. Crosstalk can be mitigated by adjusting the stack-up order and the distance between layers. Optimizing the layer sequence and the spacing in a 4-layer board is a key method for controlling crosstalk. Therefore, we recommend a layer structure of signal GND power signal. The advantage of this arrangement is that it closely couples both signal layers with the two plane layers, with L1 being close to GND and L4. And it allows for convenient return current through the GND plane. The close coupling between the GND and power planes can effectively absorb interference and provide proper reference for signals on both L1 and L4. The intermediate GND and power planes serve as a shield, greatly reducing the direct and effective interlayer crosstalk between L1 and L4, as well as the impact of interlayer spacing on interlayer coupling. The closer the signal layer is to its adjacent reference plane, either GND or power, the less crosstalk there will be, and the better the signal integrity. This is because the electromagnetic field of the signal will be more tightly confined between the signal trace and its reference plane, resulting in less energy leaking outward. That is to say, we hope that the interlayer spacing, which is marked here as 0.2, is as small as possible, and the same goes for this interlayer spacing. The smaller, the better. The radiation generated and the crosstalk signals will be quickly absorbed by the reference plane, so there will be less energy radiated outward. Theoretically, if there is no isolation plane between signal layers, the farther the distance, the less crosstalk there will be. However, in a 4-layer board, we achieve isolation through the inner planes. Therefore, the thinner the dielectric thickness between the layers and the power plane, the larger the plane capacitance formed, and the better the isolation for L1 and L4. So this means that the spacing between the two inner layers should also be as small as possible. Overall, the thinner the board, the better. For example, a thickness of 0.8 will definitely be better than 0.6 because all three interlayer spacings will be smaller, which is beneficial for reducing crosstalk. How can we control crosstalk through signal ordering and routing techniques? In addition to optimizing the layer stack-up, specific routing techniques are also extremely important. First, you need to order the signals by placing high-speed signals on the outer layers. If only two layers are used for signal routing, you should prioritize placing high-speed sensitive signals on the signal layer that is closest to a solid ground plane, which is the L1 layer. This way, you can achieve the best signal reference and impedance control. Avoid routing high-speed signals in parallel on the same signal layer, and avoid having two high-speed signals run parallel to each other for long distances. If parallel routing is unavoidable, you should increase the spacing between them. Ideally, the distance should be more than 3 times the trace width. On our board, we can also see this principle in action. First, you can see these differential pairs, which are some of the high-speed signal traces are mostly placed on the top layer with fewer on the bottom. The spacing between traces is also considered. For differential pairs, we treat each pair as a group, these two as one group, those two as another. If, for example, these groups need to be separated, we increase the spacing between the groups as much as possible. Secondly, avoid crossing plane splits. First and foremost, it is absolutely forbidden, whether for high-speed or low-speed signal traces, to cross over a split in the ground plane or power plane. This means that on the signal layer, it is strictly prohibited for any high-speed signal trace to cross over two separate plane layers. This will completely interrupt the signal's return path, causing severe impedance mismatch and resulting in significant EMI and interference. Thirdly, let's talk about via handling. First, try to minimize the number of vias, especially on high-speed signal traces, because vias introduce impedance discontinuity and signal integrity issues. Next, accompany signal vias with ground vias. If a high-speed signal must change layers through a via, place a return ground via near the signal via to ensure the return current can also follow the signal via and connect to the ground plane. This can also be seen on the board. For example, at this position, two vias are placed, and right around these two vias, ground return vias are immediately placed on the ground line. Fourth, staggered routing and isolation. When conditions allow, consider staggering parallel traces instead of aligning them completely to reduce loop area. In particularly sensitive core areas, you can use guard traces and periodically add isolation vias for further separation. For example, here in the middle, an isolation via has been added, serving the purpose of isolation and protection. Today, we took an in-depth look at crosstalk between layers in 4-layer boards and learned how to effectively control crosstalk by optimizing layer stack-up, controlling layer spacing, and using signal ordering to avoid crossing styles, among other practical techniques. Understanding and applying this knowledge is crucial for designing high-performance, highly reliable 4-layer DMI boards. I hope this content helps you become a better PCB designer. If you enjoyed this video, please subscribe to my channel for more videos. Thank you all.